But at the time this book was first written, 2008 was probably the most recent version, and SQL 92 was the most used version of SQL. And then again, but here again, basically the stuff that we're going to learn is probably stuff that was in there since the beginning. It's probably SQL 86, and the other versions have not added a whole lot to the language that we would notice, because we're using all of the oldest commands and the most used commands. But I should still say, the author still wants to say that the SQL code that they type in their textbook may not necessarily work on your local SQL system, depending on what version you have installed, implemented. And that's a timely reminder for people who use SQL inside Microsoft Access, because Microsoft added a whole bunch of extra stuff. But still, Microsoft Access will run most of what the author has here. They haven't changed the basic stuff. They just added a whole bunch of other possible function calls, which, if you tried to copy paste something that worked in Microsoft Access back into some native SQL system, it probably wouldn't work at all. Or the fancier ones wouldn't. The queries using extra stuff. But that's really the same problem you have with any tool that has multiple versions and has gotten so popular that different companies are adding different customizations to it. Is eventually the languages sort of diverge, and they don't quite work the same. They're no longer transferable between systems if they diverge too much. All right. On to the boring stuff. You thought the history was boring. Let's talk about data definition languages. SQL is a language that defines data. It's also a language that models data. It's both. But we're going to start with DDL first. Data definition language means we can use the SQL language to define the structure of things within our database. That is, we have database schemas in front of us. They are composed of tables and the fields within those tables and the connections between those tables that define how the tables are related to each other within that database. In fact, all the connections that you see between those tables, they're not necessarily all of the connections. They're just the most obvious connections. They're actually the ones that were defined when the tables were defined, but we can at any time create extra connections on the fly if we want. But okay, I'm probably getting into some weeds there. Let me back out. What does a data definition language mean? It allows that language to be able to define the schema for each relation. What does that mean? The design for each table, right? The language can also set the data types for the columns in these tables, the domain of values, data type, associated with each attribute, column. They can define the integrity constraints. That is, sometimes you want to say, well, this field cannot be empty. It cannot have the value null. And that's probably the most common integrity constraint. But there are probably others not occurring to me right now. And we can create a list of indexes for each table, and then we can set security to allow some people access to tables and other people don't see them at all, that sort of thing. And we can use these commands to say, okay, where each table is going to be stored on disks. This sort of stuff is mostly system administration stuff. We, as users, we get to use what has been set up for us by the system administrators. In fact, all of this is system administrator stuff, because usually we are not allowed edit capability to the tables in the database that we are using. But if you guys are using Microsoft Access for the project and you're creating tables and you're writing commands that create more tables, you can do that in SQL. And so you are, in a way, the system administrator of your own Microsoft Access application and files. So it is probably important for you to know some of these things. SQL is a fairly old language from back in the 1980s or so, probably even earlier, when it was developed in San Jose. But you can really see that when you see how data types are defined in SQL. Data types are defined as chars or varchars. To modern programmers, those are strings. Char is a fixed length string, so you have to say these strings will be no longer than 50 characters ever. And that's not the kind of string that we use in Python. Python lets us make our strings as long as we want, but again, this allows the database predictability, knowing exactly how much space to set aside for a string column. And so that's why it exists. Because again, remember, databases, when you give them a command to retrieve data from this table and this table and this table, and they all need to be joined in a particular way, they need to be able to do the math, like how much data is going to come from this table, and I need to join with that table, and how much time is it going to take me to do it that way? Or should I start with the third table first and bring that data and combine that with the second table and then the first? And knowing how the maximum size of your data will help it to make accurate predictions of which way to do this query will be the fastest. But of course, a lot of times when you have a last name field in a database table, you don't necessarily know what the maximum last name size should be. I mean, my last name fits in like 12 characters or so, but some people have 30 character last names, and I don't even know if 30 is enough. And so there's always fields where you don't quite know what the maximum value should be. You like having access to varchar fields? Still feels like it's got a maximum length according to that definition. That throws me for a loop. What's variable about it if there's still a maximum length? Oh! There is still a maximum length, but it could be a maximum length of 100, but each individual field might be, it could be 2 characters long or 10 characters long. It's not going to necessarily fill out the maximum amount of space, whereas chars will pad the rest of that string with spaces, and so it will always take up n slots of space. All right, moving on. We've got integers, we've got small integers. Again, an integer is going to take up more space than a small integer, but otherwise, they're basically exactly what you think they're going to be. Just like C++ has 4 or 5 sizes of integer data types, SQL has at least 2. There's probably more now, but those are the standard ones, int and small int. If you know that you're never going to count up past 1,000 or so, you know that you're saving space by choosing the small int data type. That pleases the anal retentive programmers and database administrators out there. You probably don't necessarily want to make your your auto number field a small int field, because you might hit the big time, you might have millions of users on your website, you might want to have the possibility of having big numbers in there. So you only use small int when you know that that your maximum integer size isn't going to be huge. And there again, it depends on which machine SQL is installed upon exactly what small int means. In fact, that probably goes with that goes for all of these data types. They're all sort of machine dependent, but it is a little bit annoying to know that It's really the difference between Windows computers and Macintosh computers and Unix computers, where the actual sizes of things may be different. That's where the machine dependency comes in. Numeric is how we define a floating point field. And so we have, it's a fixed point number. We know that it's going to have p digits in front of the decimal, and wait a second, user specified precision of p digits. That's a guaranteed precision of p digits after the decimal. And n digits to the right of the decimal. Where I don't even know where n is coming from here. They probably meant d. Precision of p digits. I feel like p means left of the decimal and d means right of the decimal. But now I'm going to have to read the chapter to make sure that this is a misprint, but I'm pretty sure this is a misprint. So yeah, a fixed point number is where you're going to decide, okay, all of my numbers are going to have 2 digits after the decimal, and so if you're saving a salary field, for example, inside of a table, you pretty much know that you're not going to pay people in tenths of cents, or maybe some companies do, and so maybe they'll say, okay, well, I'll keep track of your pay all the way out to the 4th decimal, but they'll say, beyond the 4th decimal, we're not going to pay attention, and so there's always going to be a decimal and then 4 digits after. So that's what a fixed point floating point number is. But then we've also got real and double precision values where the decimal is not guaranteed to be in any one place. Real, double, float, 3 versions of decimal numbers. And does it really matter which you choose? I mean, it's really what I'm just used to C++ data types. I'll gravitate towards double, especially because it doesn't force me to say where does the decimal need to be and how many digits accuracy do you need to have, and I just go with whatever the machine says is good, because unless you're doing something like astronomy or high-level engineering where you really need to keep track of 10 decimal places, then double precision data types are probably going to be good enough for us. And it's trained into my mind that double precision data types have more accuracy than single precision data types, which I feel like real might be the definition of real. But anyway, what you should be getting from this is the data types that we have available to us in SQL are pretty much the same data types that we have available to us in Python or C++, even if they all seem to have really old style names and kind of clunky parameter choices that they're forcing us to take into consideration when we have particular needs for the data that we want to store. But most of the time, the reason we have parameters like this is to allow the system to save space where it can, because the fewer bits you can store your information into the data means that all of this data that's coursing over the network and is being combined with other tables is not. It's going to make sure that any joins that need to happen are going to happen as efficiently as possible. They're all efficiency-based designs, I guess. Efficiency-based choices. So anyway, we've got a bunch of data types that are mostly familiar to us, available to us in our database tables. And really the only time where you'll have to worry about these names is if I ever force you to create a table in SQL on the CS server, which, I don't know, probably won't happen. At most, I will create data tables for you, and then you can fill them. But if you're experimenting on your own and creating your own tables, then you're going to have to choose among these, and I usually choose the data types that don't have parameters. And so I don't care if I'm wasting space, if I'm doing experiments, I'm not building huge tables anyway. I don't have to worry too much about efficiency. But okay, so let's talk about actual SQL commands that create these things. If you want to create a table named R, for example, and again, the author is using this pseudo-mathematical stuff, so R is short for relation. We just learned about relations and relational algebra, and so we're keeping R around, and we know about attributes and data types, and that's what A and D are. And basically, for every column in the table that you are creating, you need to give a name to that column. That's going to be A sub 1, and a data type for that column, D sub 1. And if you wanted to have a second column, that's A sub 2 and D sub 2, etc., etc. As many columns as you have, name, type, name, type, name, type, name, type, all separated by commas. And I guess it's name space type, all separated by commas. So the domains come from the preceding slide with those old-timey data type names. And we're not even done. That's not a closed parentheses up there. That's I left you off at the comma, because we could have a whole list of integrity constraints. We could be saying that attribute sub 1 is the primary key. That is an integrity constraint. We could be saying that attribute 2 cannot be empty. It must not be null. So there's another integrity constraint. And so we have a list after defining the columns of all the possible constraints that we want applied to this table. I guess another integrity constraint is when you have a foreign key. That is, if you are storing the ID of the student field inside this advisor table that you're creating, then you have to inform the database that this table is actually connected to this other table in some way, and so this column will have exactly the same values, and it will have the same domain of values that some other table has. That would be another integrity constraint that you would see defined within the SQL command, creating that table named R before the final parentheses closes off the entire command. Generally, if you're typing these commands in an SQL system, all of these commands are terminated by a semicolon, and so the command won't actually run until you type the semicolon and then hit return, because otherwise it's just assuming you're typing in some black window terminal window, and it assumes that if you hit the return key, you're typing in a multi-line command, because you can see just creating a table can easily be a multi-line command. Just with all the possible constraints, and probably all of your column names aren't going to fit on one line, and so that's why the basic assumption for an SQL editor is return does not mean end of the command. It's going to wait for you to actually type in the semicolon. So I believe I've talked about R, and I've talked about the capital A's and the capital D's. And so an example of this, to create the instructor table that you have in the database schema in front of you, you know that instructor table has 4 rows in it, right? And so there are 4 columns in it. And so it has an ID column. Well, that's going to be a char data type of size 5. Apparently the IDs, these are not star IDs. At BSU, we would need like char 8 or something, right? But it turns out, I don't think anybody at BSU has more than 8 characters in their star ID, and so we could easily fit our star ID field in a table of size 8. I guess this database is assuming that nobody's name will be greater than 20 characters. That's probably not going to be a first name, last name field. That's probably just, I don't know, last names, as I recall. I remember seeing some Einsteins and Mozarts in a table printout that I saw, and so Those are just going to be last names, and we're assuming nobody is going to have a last name greater than 20 characters because the maximum limit for this varchar field is going to be 20. Also, we cannot create a record inside the instructor table that has nothing in the name field. That is a constraint that is being placed right there as the A2, D2 is being defined. This could also be defined later on, but often it is nice to see that constraint right there exactly next to the value that it is constraining. So commands like that have exceptions. They can appear in multiple places. One place for readability. Our department name, again, no more than 20 characters for the name of the department. And we're defining a numeric field, and since this is salary and people are being paid in dollars and cents, and universities don't want to track tenths of pennies or thousandths of pennies, they're just saying, you know what, we're just going to track the first two digits after the decimal, and that's it. We're going to store 10 digits total. It looks like, probably, I don't think it's 6 and 2. I don't think it's total and, no, I think it's 8 digits in front of the decimal, 2 after. So however many bits that ends up being, that's how many are being reserved for the salary field. And so now, I haven't talked about the insert into command, but you might conclude from the verb insert and what is it, preposition into, that insert into inserts values into a particular table. And we are saying which table we're inserting them into. And so since this table has an ID and then a name and a department name string and a salary of some sort of floating point number, I see a string and a string and a string and a number. I am inserting values into these 4 fields in the order that they are defined. So by default, if you're not somehow naming or predefining in which order you're going to give it information, the database naturally assumes that you're going to enter in information in the same way, in the same order that the table was designed, the same way that the table appears on your schema. And I just wanted to point out that this second command, still inserting 4 values, but is saying that I don't know this person's name yet. We have an opening in the biology department, and we're going to pay that person $66,000, and we want to create a record in the database, and then we'll just change the name later. But for now, we're just going to put in null there. The database will not accept that because when we created this table, we said that we cannot insert any rows. We can't create any rows inside this table that have a null value in there for name. It's exactly what we're trying to do. We could hire somebody and not know if they're going to be in biology or chemistry. We could put a null there. We could hire somebody and not know what their star ID is going to be yet. We could hire somebody and not know how much we're going to pay them yet. Any of those other values can be null, but according to the definition of this table, the name of the instructor entity cannot be null. So, one of the most common constraints in table construction. More constraints, primary key I talked about. And again, if you define a field as a primary key, that's the same as auto number that's almost the same as auto number in Access. That is, that field will also by default be not null. But auto number, of course, creates a new number as a new row is created. And it's just going to insist that whatever field is primary key, we didn't define anything in the instructor table as primary key, but we might as well say that the instructor's name is primary key. And in that case, we would just say primary key and not null. And that would also prevent us from creating a row in that table that does not have a value in the primary key field. So both of these kind of have the same effect, but primary key really means, all of these values are going to be unique Because not null doesn't enforce uniqueness. We could have multiple Nevilles working as instructors at this university campus. Not null doesn't check against that. Primary key does. Primary key makes sure that you've got some sort of data type like in your Microsoft Access file that is auto-numbered. It guarantees uniqueness. When you're joining things together, often tables are joined on their primary keys so that you know that you're connecting to you're connecting the correct student's data, classes taken or whatever, with the correct actual student. Even if you have two students with the same last name, their star IDs should be different. In the BSU system, the star ID field is the primary key field in the student table. And so, of course, you also tell the database when you're creating a table that has values from other tables. Why would you do that? Well, because what happens if the advisor table uses instructor IDs and student IDs, and then maybe an instructor gets fired or a student drops out or goes to another university? If that student record needs to be for some reason deleted from the table. I mean, I don't think in a university database student records get deleted very much, although they probably get shunted from one table to another, current students versus old students or whatever. But foreign keys are important in that, since data in one table is strongly related to that very same data value that came from another table. If that row from that other table ever gets deleted, then wherever it's being referenced from has nothing to reference anymore. If we're using somebody's student ID in the advisor table, and then that student's ID, student's row gets deleted from the student table, you're stuck with an advisor-advisee relationship referring to a student ID that doesn't exist in the student table anymore. It doesn't have anything to connect to. So the database needs to know which are the foreign keys so that if rows do get deleted from the tables that are being referenced, then that information is communicated to the referencing tables so that the rows referencing to that value are also deleted, so that there will be no mistakes, no unexpected crashes happening when you try to connect a value in one table to a non-existent value in another table. Basically, by saying that you have a foreign key column in a table, you're guaranteeing that whatever value is in that column is in some other table in your system. And so these constraints are often used for if something happens to the source row in this table, then other things need to happen that the user did not ask for, but other parts of the database do need to be updated. So, okay, now we're going to, for whatever reason, we're going to modify our table build. So I guess we deleted the old instructor table because we decided not only do we need the name field to not be empty, but we want to make sure that the star ID field is a primary key, because we know that every instructor is going to have their own unique star ID. That way, if we have two Nevilles or two Einsteins working on campus, we'll be able to tell the difference between the two. And also, we're going to allow the value in the department field to come from the same universe of values that is stored within the department name field, to come from the same universe of values that exists within the department table. And again, since department name is a foreign key in the instructor table. It actually comes from the values that are in the department table. If ever the computer science department is mothballed at this university and the computer science row gets deleted from the department table, then they're going to make sure that any instructors that taught in the computer science department that still had to have their department name as computer science, those rows will be deleted from the instructor table, just so, again, the database remains consistent. So, just so there are no records looking for matches that don't have anything to match to. It probably indicates that we're using pointers to in our table, or under the hood, the database is using pointers, and it's not actually storing the computer science string inside the instructor table. It's a pointer pointing to where the string computer science resides somewhere else in the computer. And again, if that record is gone, then that pointer is pointing at nonsense. I've never created a database myself. I just made up that last theory, but the way that the way that the database people, database administrators are just so wrapped up with efficiency, I wouldn't be surprised if modern day databases were heavily pointer dependent like this, and that is why they're taking so much care to maintain consistency in a database. They don't want the values that are pointed to by pointers to disappear without some cleanup happening, so that we don't get any, I don't know if you guys have ever got any null pointer errors in your C++ programming adventures, but that's the sort of annoying thing that the database designers are trying to protect us from. And like I said before, when you declare a field to be a primary key, that automatically means that it will also have the not null constraint upon it. So, okay, I see a couple more tables on your database schema in front of you. If I were creating the student table right now using SQL code words, the code words, by the way, the keywords are all the bold words here. Often when I type SQL commands, so that readers can tell the difference between the keywords and the variable names that I'm using, I will type the keywords in all caps. And the only reason I do that is because when I read other people's SQL code, that's what they did. But it does make it easy to tell the difference between the keywords create table, and then we know that this word isn't a keyword, this word isn't a keyword. These are the variable names that we're creating. So when the students were created, they also had a 5-character ID. They also can't have a null value for their ID value, and they've also got a pointer in this field pointing to a specific value stored in the department table. And so basically every arrow and arrow line and arrowhead that you see on your database schema in front of you is basically tracking all of the foreign key declarations that were made when these tables were initially constructed and designed. That's where those arrows are coming from. Takes! Oh my gosh, well, what are the arrows coming out of the takes table, and what are they pointing at? Well, I bet one of those arrows is pointing at the ID field in the student table, and then there's like 4 matching arrows that go from course ID and section ID and semester and year, all pointing to 4 similarly named rows in the section table design. But the takes table is this: the student with this ID is taking this course, this section during this semester and this year, and at the end of that semester they will be given this grade. And so this grade at the beginning of the semester, that grade is probably null because it doesn't get filled in until the professor sends in grades after the final exam. So that grade field is not defined, explicitly not defined as a null field. It would make that table design kind of useless if, as soon as a student signed up for a course to take during the semester, a not null grade value had to be provided. Any questions on these? Do you see the connection between this code here and those table designs in front of you? The author is showing you the SQL commands that author used to create the tables that they then filled with data to use as illustration for all of the examples in the book. And typically what I often do is I create an account for all the students in this class on the CS server so that you can go in and test these commands out yourself and pull out the data from this database. Now, the data in this database is a little bit boring. The names of the professors are things like Mozart and Einstein and stuff like that, and the names of the students are somewhat generic, but you see how this thing works in real life, typing in these commands with your own fingers. And again, you usually don't have to type in commands that are quite this long because the longest commands do tend to be the ones that are creating the design of the thing. The commands that we typically use, show me all of the students in the CS 3507 class, is going to be, it's still going to be like 2 or 3 lines long, but not necessarily as many lines as this is. All right, what else? So, some more designs. I've got a course table. The course ID is going to be the primary key there. That means not null. Otherwise, up to 50 characters for the title of the course. Department name. Oh, that's also a pointer that's pointing back to some data in the department table. And credits, again, that's going to be a floating point number. And I guess we're not allowed half credits or whatever, so there's going to be 0 digits after the decimal and no more than 2 digits in front of the decimal. No more than 99 credits per class, I guess. And again, we probably saw primary key defined down here, but often primary key constraint is defined right next to the field that is being defined as the primary key. Where did we? Yeah, we saw that down here where primary key said, look up here for ID. And here it sort of makes sense that primary key is down here because it's actually combining 1, 2, 3, 4, 5 different fields. And so there's no one field that we can put primary key next to. Why would we define a primary key over 5 fields? It's probably because each individual field is not necessarily unique when we're considering a student taking a class. I mean, a class can occur during multiple semesters. It can be given during multiple years, and so it can have multiple sections. So if you're trying to determine which class this student is actually taking, for CS 3507, you have to say that it's fall of 2025, section 1, and that distinguishes it from any other student who may be taking section 2 of CS 3507 in fall of 25, or in this case, since they maintain historical data in the same table, all of the other students who have taken CS 3507 in the past. And so basically, by combining these 5 values together, that generates something that's unique. Oh, I called that a candidate key before, right? We know that a primary key can only be based on a collection of values that taken together uniquely define something. So that's what's happening right here. All right. Any questions on any of that? I'm not quite sure what's coming up. Sure, why not? think that blank page told me that I stopped at that slide in earlier semesters, and yeah, I'm right about on schedule. I've only got about 6 minutes left, but let me keep on going through, I don't know, the administration commands anyway. Drop table, probably not a command you want to use a whole lot, but again, if you are messing around with your own database, you might realize, oh, I didn't create a table with enough columns, or I didn't define the proper column to be the primary key, and so when you're creating tables, you might be dropping tables a lot. It's just once you have 1,000 rows of data in those tables, you probably don't want to be using the drop table command a whole lot at that point, because drop table and then followed by table name is going to not only destroy the table, but all of its contents, all of its records. Delete from is different from drop in that it leaves the table structure alone, because remember, that's probably the most difficult part of table creation, is figuring out where all the primary key definitions should be, all the not null constraints, any foreign keys that you might want to provide to the system to help it be efficient so it can track values via pointer rather than copying the same string value in multiple places in your database. And delete from is going to empty out a table but not destroy the structure. You are, if you're not adding anything extra to that command, usually there's a few more code words that you can add to be more specific, but if there's no additional predicates to this command, that is going to delete star from student. It deletes everything from the student table. But at least the student table will remain behind. More often, if you've gone to all the trouble of typing in like 10 lines of a create table code and you decide, oh, I didn't want field 1 to be the primary key, I needed field 2 to be the primary key. Instead of retyping all that stuff again, you can just say, hey, go back in and change the design in this way. Let's alter this table named R and add an extra column of a given data type, for example, that I forgot to do before, that I didn't think to do in the original creation command. So you can add columns to a table, you can remove columns from a table. Here we're using the drop keyword again, but that's not dropping the entire table. We're altering table R, and we're actually dropping an attribute. We're dropping a column out of that table. Then again, when this book was written, not all SQL databases allow you to drop columns, but Microsoft Access will allow you to, and probably most modern database applications that you use will allow you to modify your table designs relatively problem-free. This feels like a problem that maybe I grew up with way back in the 80s when at the beginning of the world. Okay, you know what? I think this is going to be a good place to stop because we're moving from database design language to database modeling language. Again, it's the same language, but now the commands are going to be doing other things, and mostly they're going to be doing the same things that we've been learning about in relational algebra. We never really talked about any relational algebra operators for creating relations and things, and so because I guess probably the mathematicians, these data modeling commands, they only tend to be run once or twice or 3 times over the lifetime of a project. What really matters is when we're pulling data out of a table or something. So that's probably why the mathematicians didn't model those things. And now we're going to move on to SQL commands that tie in more directly to those Greek letters that we've been using for the past couple of weeks. That being said, I do want to again remind everyone that today is the only day we're having this class this week. I'll be out of town Wednesday through Friday this week. Next Monday, the school itself is canceling class. No class on this campus on Monday because of Columbus Day. And so Wednesday will be the only day next week that we have this class because I'll be out of town again on Friday, what with the DigiKey people thing. And so, yeah, one class this week, one class next week. Thank you very much for your attention. Have a good weekend. I will see you guys again on Wednesday.